a real special honor for me to receive this award, and I'm very sorry that I couldn't be there in person. But I'm real excited to tell you about some of the work we've been doing at University of Washington to increase students' confidence and efficacy in research skills. Today, I'll tell you about a class that we have developed that's a type of class called a course-based undergraduate research experience, or CURE for short. And in our case, the CURE uses Arabidopsis as a model system. And I just want to acknowledge before starting the huge body of work that has gone into identifying the elements of cures that are critical for student learning, as well as the broader Arabidopsis community for developing all of the resources and tools that our students can use in the classrooms to use Arabidopsis to learn about research. So why are we interested in this topic? If we look at who is receiving PhDs in biology, we see huge racial and ethnic inequities. So even though our Black and Hispanic and white students are declaring STEM majors at similar rates, we see large discrepancies at who is receiving PhDs. So, for example, although Black Americans make up 14% of the population, only 3% and 5% respectively of PhDs are awarded to Black students in agricultural fields and biology. In this case, biology includes the medical sciences as well. And there's many reasons for this inequity, this observed inequity, that I won't have time to talk about today, including systemic racial inequities in educational opportunities, as well as pervasive non-inclusive environments in STEM. But today I wanted to tell you about something that we can do at in higher education, at the college level, to try and address this inequity in terms of increasing students' self-efficacy in research. So what do we mean by self-efficacy? This comes out of social cognitive theory, where it is essentially the belief that you can really succeed in a particular task. And it's important to recognize that this is task specific. So I may have high self-efficacy at teaching biology and low self-efficacy at flying a plane. So it's different for different tasks, but also importantly is not fixed and can change with experiences and training. So why is it important? Much research, I've just listed a few here, has shown that student self-efficacy in a particular area can impact how well they do in that area, their sense of belonging in that area, and whether they choose a particular career or not, as well as their persistence in that particular career. So self-efficacy has been shown to be one of the predictors in science. Self-efficacy has been shown to be one of the predictors in whether students choose STEM majors and stay in STEM majors. So what can we do in college to increase self-efficacy? One thing is just getting hands-on experience with research. And traditionally, this has been done in faculty members' labs, and where students can gain important skills by joining a lab. However, we do know that disproportionately benefits students that are continuing generation students coming from well-resourced communities. And so what we would like to do is actually develop, by using cures, these course-based research experiences, we can democratize access to the research experience. And one of the things that cures do is they really focus on mastery of skills rather than on performance, and that can increase students' sense of control over their learning. Also address novel scientific questions, often socially relevant, which can actually increase the value that students place on learning research. And also by giving them control over these experiments that they're doing, that can provide a sense of ownership. Importantly, there's many opportunities built in for iteration and troubleshooting, and this can normalize failure as really a essential part of science, and can help students learn some skills that will help them overcome hurdles when faced later in science, that can help them persist. And also, importantly, these involve a lot of collaborative skills, working either with peers in the class or externally. So what does our particular cure look like? I'm not going to go into a lot of detail here, but we're using observations from the literature about how Arabidopsis responds to changes in its environment, to change gene expression, to respond to those stresses. And we focus on one particular epigenetic regulator called histone acetyltransferase 1, and what role it may have in mediating these stress responses. So the students develop a specific hypothesis based on the literature. They all use Arabidopsis as a model system. They all use tDNA insertion mutants as part of their experimental design. But then they develop the other aspects of the design in terms of what stress they're going to measure, the timing which they're going to take the stresses, what genes they're going to look at, et cetera. And they all use gene expression as a measure. So when one is designing a class, we all know what one of the difficult questions is what learning outcomes you want students to gain from the class. So we drew on national recommendations for what we want our students to know and be able to do by the time they graduate. This comes out of a report called Vision and Change from many years ago now, which identified focus on core ideas and core competencies that we want our students to gain by the time they graduate. We also drew on a resource that we developed in our group called the BioSkills Guide, which you can download here with this QR code, which really just identifies the specific learning outcomes at the course and program level for these different competencies. And I'm just going to focus on two of the competencies today because we saw different student self-efficacy with these two. So process of science and quantitative reasoning. How do we measure science self-efficacy? One measure we have used is a pre-post survey where students self-report their level of confidence on a Likert scale from very unconfident to very confident. And then we look at change over the quarter. So you can see if somebody loses confidence, be a minus number there versus gaining confidence. So we are, of course, hoping to see students kind of shift to the right in terms of their confidence level. So let's look at the first competency is process of science. One of the specific learning outcomes for this competency is hypothesis development. We develop in this case, students are asked to develop a predictive model illustrating how this HAC1 factor mediates the abiotic stress. And here we're just seeing examples for different stresses of drought and cold. So with practice like this, how does this change students' confidence and their ability to ask a meaningful question? Well, we see a nice shift over to the right in terms of students gaining confidence. You can actually just see the absolute levels here. They came in with pretty high confidence. I should have said these are senior level students generally, so they've had a lot of experience prior, but then they still see an increase over the quarter. So that is encouraging and is actually the pattern that we see for most of the learning outcomes that we look at in this class. Looking at another competency, quantitative reasoning. In this case, in our class, we focus more on things like performing basic calculations, like dilutions, or making up molar solutions, and interpreting biological meaning. So what do you learn about RNA purity from the numbers, the absorbance numbers on the spectrophotometer? So what do our students say about their confidence level as they go? So here we see a different pattern. So we see some students who are gaining confidence or staying the same, but a significant number who are actually decreasing in confidence. So this is concerning, and we want to figure out what is actually going on. These are the numbers we can see here. They're starting out lower than before and then decreasing. And we do know that many of our biology students enter biology because they say they don't want to work with numbers. That's why they chose biology. So they're not understanding the value of quantitative reasoning in their research. And when we look at who are in these different groups of students who are increasing in confidence versus decreasing confidence, there's no difference in gender, racial, ethnicity groups. But one factor we do see that's different is that the students who are gaining confidence are those students who came in with previous research experience in a faculty member's lab. So they may understand more the value of quantitative reasoning and be willing more to invest in learning those skills. But we really need to think about what's happening in the group dynamics, in the comparisons maybe that students are making, where they're actually seeing that they have less confidence after potentially comparing themselves to others in the group. So we're working on different activities we can do to actually normalize this experience, but also maybe draw on the resources of the students who have research experiences to help them share the value they see in quantitative reasoning. So today, just to summarize, I've talked to you about how self-efficacy is an important predictor of persistence and resilience in a particular career, and how we have shown, as well as many others have shown, how these cures, these course research experiences can actually build student self-efficacy in these key science competencies. And importantly, by monitoring changes in the student self-efficacy aspects, we can that can give us insight into what we need to do in our classes to make sure that we are maximizing student gain and self-efficacy across all of the core competencies. And I just want to end by acknowledging all the people who have made this possible. Particularly want to thank the NAASC for creating this award and for honoring our work at UW with this award. We really appreciate it. And also the current and past teaching members, including our peer facilitators who help out with this class. And many of the people involved in this class are actually there at the meeting as well, including members of Adam Steinbrenner and Jennifer Nemhauser's group. We also want to just thank the broader Arabidopsis community, as I said, for developing all these tools that we use in the class, and our undergraduates as well, of course. And if you have any questions, since I couldn't be there in person, I've put my contact information here so that you can reach out if you have any questions. Thank you very much.